Right, class. Welcome to the series of Verilog lectures. So this series of lectures is to complement the already finished Verilog tutorial, and from the feedback, class feedback, most of you had asked for extra Verilog lectures. So what I plan to do is to write Verilog and write a bunch of examples, and hopefully most of these examples will be enough for you to get a good grasp on at least some basic Verilog concepts. In this video lecture, what I will do is write two kinds of code for the XOR gate. One is behavioral and other one is structural. Also, I will write a test bench for this XOR gate, and then basically simulate both of these, the gate module and the test bench, and then we will see how we can observe the outputs, observe the working of this particular Verilog module. Right, so HDL, two kinds of HDL can be written. We will consider two kinds of HDL. One is behavioral. In the behavioral code, the modeling or the model is expressed in terms of equations or in terms of the truth table only. Basically, only the functionality is modeled. So behavioral, or you could say the code is functional in description. And the other kind is the structural code, and the structural code actually is actually the description, the gate level description, or even the transistor level description. So it can be the gate level description of the circuit, or it can be the transistor level description of the circuit, where it is basically a lot of information is there beyond just the module itself. There is a lot more hierarchy of information inside a structural model. So you can contrast both of these even in this slide. So the behavioral description of the half adder is basically the sum equation, the carry equation here. The other description of the half adder is basically the truth table, where x and y are 1-bit inputs, and the sum is the sum of x and y bits, and the carry that is generated after the sum for 1 1. The equivalent circuit, that is the gate level description of gate level circuit of the half adder, is also shown here. Right, so we can write Verilog in both of these expressions. Right, we can express half adder in both of these. The example that we will consider for the first Verilog code is the XOR gate, and of course you all know what the XOR gate. I've taken XOR gate because XOR gate has this equation that we can express in Verilog. I could have equivalently taken an AND gate or an OR gate, but XOR gate is actually giving some descriptive ability to write. So this will be the functional description of XOR gate. This is what we will write in the behavioral code. Right. The structural code is basically just this much. The structure of XOR gate is just one XOR gate, and yeah, we will see that it's fairly straightforward to do this in Verilog. Right. Before we actually begin coding in Verilog, it is always helpful to write. First of all, it's always helpful to, of course, write the gate level diagram and reduce your truth tables down to simplistic equations, the most simplified form equations, and so on. However, what is also useful is to have a clear idea of what the final circuit looks like, and that can be in an abstract manner shown in a block diagram. And you have already seen a bunch of block diagrams. So for the XOR gate block diagram, to consider a fairly simple sort of block diagram, the XOR gate has 2 inputs and 1 output. Of course, you know that this is a gate, and this is not the representation of the gate, whereas let's say this was even any other circuit. It was a bigger circuit than all of those. Any of the circuits that you would want to design can be represented in as an interconnection of a bunch of components, as an interconnection of a bunch of modules, and that sort of representation is very important before you begin to write Verilog, because Verilog allows you to describe your circuit in terms of these modules. So first of all, it's useful to write the block diagram of the underlying component that you're modeling. In this case, it is XOR, and let me just name the inputs as A and B, and maybe the output is Y. So behaviorally, I know what y should be. The output y is governed by this equation, a bar b plus a b bar. This is because I plan to write the behavioral code. Of course, you could also say that a XOR b is equal to y, but so there's two different pieces of code. So I will write code number 1, which describes this XOR gate or this module as y equals a bar b or a b bar. Second piece of code I write that is basically saying y is the XOR gate. Right. This is the first thing that we need, and in our design right now for the XOR gate, it's because it's very simple. There's just one module. There is no modules inside. There are no sub modules. Which we will see later. We will build something which has a bunch of sub modules also, but this being the first example, let's begin. Any module that you design has to be in Verilog has to be defined inside these keywords module and end module. So Verilog is basically around 100 odd keywords are provided, which help one describe any digital circuit. Okay, so module and end module are the first keywords that you're looking at. This is the syntax of defining a module or declaration of a module. So basically you start with a module keyword, give it a name, and write down the sequence of inputs and outputs. In either way, I've written outputs comma inputs. That is a convention. So you can you can compare this to a function declaration. It looks very similar to a function declaration with some minor changes. So let's begin writing the Verilog behavioral code for the XOR gate. And what is shown here is, of course, the module and the end module keywords, and the name of this module is called XOR _gate, and this is one output y and a comma b. So now I hope you can relate back to the block diagram, right? The block diagram basically was written in this manner, a and b being the inputs and y being the output, and this module was called XOR _gate, and so that's what we have just written down. Now let's begin. So once this begin and end module, so you don't have to write a begin and end, so it's automatically module, the line module itself sort of indicates begin, and this is end. Note that there is a semicolon at the end of module line. So each module contains these three parts. First is the IO port declarations, the input output port declarations, and here we know the input output ports, right? So we will be declaring the input output ports here. Then if there are any inside the module local wires or other circuit elements, then those declarations will go here, and then the final behavior itself. And for this simple XOR gate, there are two inputs, that's the A and the B input, and there is one output Y. And of course the behavior we've already sort of figured out. The behavior will have some form of the equation, that was y equals a bar b or a b bar, which is expressed in the correct Verilog form. That will form the part of the behavioral code. So every module will have these three parts in its Verilog model. So let's go ahead and fill in these parts of the module. So first of all, it's the IO port declarations. Fairly straightforward to do this. All the input ports should be declared as input, and there are two of these, so I just so input A comma B, and all the output ports have to be listed, so output Y, and that's just one output. And for this XOR gate, that's done. That's about it. There are single bit values, so this A and B are just 1 bit values, 1 bit quantities or 1 bit elements, so to speak, right? So we're not using any array notation here, it's just 1 bit, that's why just A and B. There are no local nets inside the behavioral description, so this part will be empty, but of course the structural code will have some local net, as we will see later. So before we go ahead writing the behavioral code, a couple of points about the input and output keywords. These are the two next new keywords that you've just seen, input and output. One obvious thing is that the input keyword declares input ports and output keyword declares output ports. More information has to be more background information has to be gathered here. What happens when we what do we understand by an input port is that there will be some circuit element over here that will be sending signals to this input port, or as is said conventionally, is this circuit element is said to be driving these input signals. So there will usually be a previous it could be another gate, for example, right? So it could be another gate, or it could be another completely bigger circuit, or it could be just a bunch of registers or flops. There will be some sort of driver here, so there will be some sort of driver which will all be driving these inputs, right? Similarly, this output Y will drive some other circuit element later. So that's something that you have to understand. So, so you can assume that this input and output keywords are creating what are called as wires. In fact, this wire is another keyword. So all circuit elements in Verilog fall under two categories. They are either wires or they can be declared as reg. So let's just look at what a wire is. The wire declaration was modeled to be an equivalent of a wire on the breadboard that you might have you have used in your lab. So basically, the wire can be used to interconnect two circuit elements. So for example, if there is so there are a bunch of gates, and if you wanted to feed the output of each of these gates to another gate, this is a wire. So we declare this circuit element as a wire, right? The property of the wire is that it does not have any memory, so it does not it cannot store values, and it is not able to sort of recall values. So basically, another way of saying it is it does not have any state. And you have heard this already in the context of inputs and outputs. It is driven by other circuit elements. It does not generate logic of its own. It gets driven by other circuit elements which are connected to it. And so the input output keywords create wires, right? Create nets of the type wires. Contrast this with the reg, right? Reg has memory and it can drive a wire. And reg is a circuit element that can be used to build sequential elements, and wires can be used to build combinational elements only. And we will use wires in the modeling of the behavioral code now. Yeah, let's begin modeling let's complete this module now. So we have finished declaration of the ports. There are no local nets inside this module. Inside the module, there are no new wires required because we are going to just write the behavioral code. And the behavioral code is basically just this much. Verilog allows you to express the Boolean equation, right, directly. So this is not of A and B, or A ampersand not of B, right? So this notation is very similar to C. C programming notation, where each of these, this is the not, or this is the tilde, and this is the ampersand, right, and this is the OR, bitwise OR operator. Let me just like, this is bitwise AND operator, right. There is one more, there is an additional piece of information that has to be added to this file. Whenever we want to drive a wire element, this is Y is a wire element. Whenever we want to drive a value inside the wire, this keyword assign has to be given, and what we are asking Verilog, or what we are asking Verilog simulation to do, is to drive this wire Y using this logic, that says not of A and B, or A and not of B, right. So this is the other keyword that you're looking at now. So assigns. Here, this is all that has to be done to model the XOR gate. And let's see. So this is the final code, and this is what the code will look like. And once you've coded up this this much, you have now created the XOR gate. Just go ahead and save this file as a .v. So for example, you could create this and then just call it XOR gate.v. Usually it is convention to actually name the .v, which is the Verilog file, after the name of the module that is written inside this. So you could also call this, but that's just a convention. It's your choice. You could also call it XOR_gate.v, and that's it. So we have now modeled the XOR gate. Yeah, so there is a slide on what assign is. So let me just go ahead and create a XOR gate, same gate that we've been talking about. Module XOR_gate, input A, B, output is Y, and net declarations here, and these are IO port declarations, right, and of course the behavior is assign Y equals A and B, or B, A and B. That's it. This is it. So once you've done this, so I have saved it as XOR_gate_1. If you have installed iVerilog, let me see, XOR_gate1. Yeah, that's it. It did not give me any error here, so it's been coded correctly. Yeah, so I will go ahead and write the structural form of this gate also. So this is XOR gate under one underscore one. So let me just make it XOR underscore gate 2.v. Right. So this is structural. So this underscore s here. For the behavioral, just call it underscore 1. Right. So underscore XOR gate, and what I want is the structural code. What will change in the structural code is we are writing the gate level circuit in the structural code. So this will not be, so the behavior is not what I want. What I actually want is, so there are two AND gates here. The first AND gate is fed, so the gate level diagram of the XOR gate will be like this. Right? There are two AND gates. The first AND gate describes not A and B, right? The second AND gate will achieve this part of the equation, and then both of the outputs of these AND gates will be fed to the OR gate over here. So let me just feed that for a moment, right? So this is something that we've already done. Sorry. Structural. Yeah, so I'm trying to do structural. So the structure of the XOR gate will just look like this, right? Two AND gates and fed to an OR gate. The first AND gate will be fed with A and B. The second AND gate will be fed with the A and B part, right? That's it. And we will code this inside Verilog, this structure. The other way of structural coding is you just write XOR y comma a comma b. That's also possible because XOR is also a keyword in Verilog, but we will do a little more, right? We will try this one. Now, if you again encapsulate this inside a module, then it is the same two inputs and one output y. However, inside this module, there are 3 gates and there are 2 wires here. So inside the circuit we are creating 2 wire elements. So let's say I call this W1 for wire 1 and this is W2 for wire 2. Apart from this, we are going to use an AND gate, so 2 AND gates, right, and also an OR gate here, right. For the AND and the OR gates, I will use the keywords. I will use the inbuilt gates themselves, but you could separately write AND gate code, right? As we've written for XOR gate, you could separately write AND gate code and also use them as submodules, but that's just for later. So what I plan to do in this structural code is to just use the inbuilt AND gates and the OR gates, create 2 wires which will be the local nets for this XOR gate, and yeah, that will build the XOR gate. So let me just go to the editor. Yeah, so this is the structural code that we want to write. Yeah, so what I want is behavior is this structure. What I want to do is this structure will contain 2 AND gates feed to 1 OR gate based on the diagram that we've just written. So let me do that. Before that, of course, we need local nets. We need 2 local wires which will feed the output of the first AND gate as the first input to the OR gate and the output of the second AND gate as the second input to the OR gate. So what all I have to do is just write wire. I will use just W1 and W2 for the 2 intermediate wires. And let's do this. So and the syntax for doing this is the output comes first and the inputs come next. So one of the first AND gate should be fed with the NOT of A and B. So let me just do that, NOT A and B. So that's one AND gate, and the second AND gate will be fed A and NOT of B, and its output will be drawn out of wire 2. Now I will feed them both to the OR gate, and OR gate, the inputs will be wire 1 and wire 2, and the output will be equal to Y directly. So if you just feed it, so the Y output will be driven by this OR gate, and you also should note that this wire W1 is driven by this AND gate. Similarly, wire W2 is driven by this AND gate. So these 3 lines, right, using 3 gates and 2 local wires W1 and W2 will be able to will correctly define structurally an XOR gate. So let me just compile this to see if this works. So let me see what I've done. So yeah, so Verilog XOR underscore gate 2.v. Okay, that's compiled correctly. So we have this is just one other way of writing. So I could just write XOR. So for example, I could just write XOR y comma a comma b. This is also there in Verilog. This is also allowed, so we could probably do this also. Another way of doing this is I could create a submodule named AND. So for example, let's say I had written code for AND gate, and what I would do at that when I had done that is, let's say I had written code called AND gate, then I could create a submodule, and we will say, for example, just say G1. Right now, so there are two expressions of the XOR gate, two models of the XOR gate. One is the behavioral, I just underscore B, say behavioral code, and the other one is a structural code, which is just one possible way of writing the structure, two AND gates and one AND gates. Right. Okay, so